Most of the videos today talk about practical details of measuring S parameters, but in this video we're going to introduce one bit of useful theory that helps us understand measurement errors. So let's imagine that we decide to put two two-port networks in a row, which might happen if we decide to cascade some amplifiers. We'll call the first network SX and the second SY, and we're calling them that because we're describing the two ports using S parameters. It's common to describe high-frequency networks with S parameters because they're easy to measure, and most high-frequency components will give you a set of S parameters in the datasheet. I've drawn that situation on this slide, and it looks okay thus far. Each S network has its own set of A and B vectors, and the A and B vectors are related by the S matrices at each two-port. But there's an annoying sticking point if we want to combine these S parameter networks into one big matrix description. For instance, if we want to find the total gain of our two amplifiers. We have to do some footwork with A2X, B2X, A1Y, and B1Y. The waves are clearly related to one another, but not in a clean way. For instance, it looks like B2X becomes A2Y. So we might need to do some kind of rotation or transposition matrix between SX and SY if we want to relate A1X and B1X to A2Y and B2Y. That's annoying, but the heart of the problem is that the S parameter matrices assume that waves are always coming into them and then bouncing off of them, scattering. And rearranging the matrix might make this analysis easier. This is where T parameters come in. T parameters, or transfer parameters, rearrange the A and B waves that are in the S parameter matrix so that the T matrix describes the behavior at port 2 in terms of the waves at port 1. You can use a T parameter matrix to propagate waves from one side of a two-port to the other. And we'll see how on the next slide. And as a quick note, this definition might look backwards to you. The matrix is transforming the B2A2 signals on the right side of the picture to the B1A1 signals on the left, and we're used to seeing signals or transformations flow from left to right. This convention makes some S parameter to T parameter conversion math a little easier, which is why we use it here. But it's important to remember that a T parameter matrix will propagate signals from port 2 to port 1, which is to the left in our drawings. I've rewritten the matrix descriptions of our two ports as T parameters on this slide. So let's assume we're still trying to find any linear matrix that relates A1X and B1X to A2Y and B2Y. We might start with the sticky spot we identified on the previous slide. We can write the relationship between A2X, B2X, and A1Y, B1Y waves that arises from the middle transmission line as a vector equation. Here we see the relationship I talked about on the previous page, where A1Y is equal to B2X. Each of the vectors in this equation appears in our T parameter definitions above, so we can plug the T parameter matrices times the outermost A1X, B1X, and A2Y, B2Y vectors to propagate our equation from the middle line to the outermost ports. This step shows how we can use T matrices to move wave relationships across a network, which we can't do with S parameters. We've taken the relationship in the middle of our network and propagated it outward across the T matrices. This is especially clear on the left side of the equation where the T matrix times the port 2 signals replaces the port 1 signals, effectively moving the port 2 signals at the very right side of the screen to the left to the middle line. On the right side, we had to use a matrix inverse because we want to imagine our port 1 signals going to port 2, but the principle is the same. We can multiply both sides by the inverse of the T matrices to make the TX matrix to make this equation a bit clearer. And in doing so, we reveal how to achieve our goal of merging Tx and Ty into a single matrix. The combined transfer matrix that takes B2y, A2y as an input and produces B1x, A1x is Tx times Ty. Here we multiply individual transfer matrices right to left, which is the opposite direction of the port 2 to port 1 signal flow from A2y, B2y back to A1x, B1x. I call this out because my memory tool for remembering the direction that you multiply the T matrices is noting that I need to apply Ty to A2y, B2y first, and then Tx, and that matrices are applied to a vector from right to left. Like all linear descriptions, there are transforms between T parameters and S parameters, and I've included those here. These could be used to turn our T cascade from the previous page into an S parameter description of the combined amplifier network. I've also got two quick asides to mention. The first is that there's a low frequency version of T parameters that plays well with our Z and Y parameters. These are called ABCD parameters, and their definition is given here. And the second is that there's an alternate definition for T parameters. We spent a lot of time noting that our T matrix definition propagated signals from port 2 to port 1, but there's an alternate definition that propagates signals from port 1 to port 2, and I've included it here. So in summary, T parameters relate port 1 to port 2 instead of describing reflections at each port like S parameters, and I've put the definition matrix on this slide. Multiplying AB vector by T parameters will move that signal from port 2 to port 1. Cascaded T parameter networks multiply, so T cascade is equal to Tx times Ty in our example in this video set. And there are T to S and S to T conversion formulas.